Okay, this next question asks, when does the particle speed up? We have to be very careful with the wording here. Speed up would mean that the speed is increasing. Okay? Does not mean necessarily that the velocity is increasing. The speeds are getting greater. Okay, so to do this, we are going to have to look at the derivative graph, but we're going to have to look at its absolute value. Okay, so the derivative for this function can be found by hand, and it is velocity equals 12t cubed, 12 what? 12t squared minus 64 t plus 73. So it's just the derivative. Okay, the speed is increasing would mean that, so it means that absolute value of v of t is increasing. Okay, so I'm going to go and do an indoor graph. My calculator can do graphs of derivatives, remember. But I'm going to actually have my calculator do an absolute value version of it. So let's go to the graphing calculator. Okay, so here's my function. Now I'm going to have a velocity graph if I do the math 8 and then that thing. So I'm going to actually have to first go to catalog absolute value and then do math 8. So there's ender. I need to put y1 here, so that's vars function. So it's absolute value of numerical derivative of y1, comma, the variable x, so we're differentiating with respect to x, and we're going to find the numerical derivatives at all values of x. End graph. Okay, there's our original function. I've reset the window to zoom standard. And here comes my speed graph. And here would be a suitable window to change it to. You can pause it and enter that if you like. It's the window we had before. And here it's graphing my speed graph. Okay, so where is the speed increasing? Well, the speed is increasing on these two intervals, right in here and here. Okay, so I'm going to have to find those points. Okay, so first I'm going to go ahead and make my second plot bold. And I think I'm actually going to turn off my first plot. Let me just abort that. I'm going to turn off the first plot. Okay, so here's my graph. Looks like right around the 1.6 second or so, up to about the maybe 1.8 second or something, and then starting at right around the 3.8 second, it goes up from there. Okay, so I need some points. So I'm going to do CALC minimum in this region. And I got 1.653. That sounds familiar. Okay, the y value here, this is basically 0, if you ever see that, 10 to the minus 5. Okay, let's go find some other points. Let's go find this maximum in here, right bound, left bound, right bound, a little guess right there. Okay, this is at 2.666 seconds. In this region, we have the speed increasing. Okay, going back to the graph. Okay, I'd like to also find this minimum point over here. .68. Sound familiar? So from t equals 3.68 and onward, it is speeding up. Okay, so maybe this is not what you expected. And now, I will admit something. The phrasing here, speeding up and slowing down, could come across as confusing. For something to speed up, you would think the velocity would be increasing. But actually, it would mean the speed is increasing. We're going to talk more later about how you can always nail this and not mess it up. But the absolute value graph helps a lot to see that. Okay, where is the velocity increasing? That's a different question. For that, we'll take off the absolute values and look at the graph for velocity. Okay, then it says, when does the particle change direction? We actually already talked about that. That was at t equals 1.653 and t equals 3.680. When is the particle at rest? That's the same question. At t equals 1.653 and t equals 3.680 seconds. So it's at any time when the direction reversed. That's when it would have to stop instantaneously. So you probably want to put instantaneously. Okay, now we're asked to describe the velocity and the speed of the particle. So I'm going to actually go back to my graphing calculator, and I'm going to remove the absolute values. And that this point right here is the 2.666 seconds. It was actually up here a minute ago, right? So I'm not going to recalculate it. I already know. Okay, so let's talk about the velocity. So the velocity was decreasing, so we're taking this very literally now. The velocity is simply decreasing until t equals 2.666 seconds, and increasing after that. So we can write that. This portion was above the x-axis, so the velocity was in the positive direction, but it was decreasing. So the velocity was positive but decreasing until the 1.653. It then became negative, which means it switched directions. Or I'm sorry, it then became negative, which means it switched directions. And then it ended up bottoming out. So let's go and write this in before we have to say it and then remember what we said. So let's go over here. Okay. The particle started with a positive but decreasing velocity. And then we'll stay away from the word it. The velocity became negative, and then started increasing. So the velocity became negative, and then started increasing. It became positive again. Increased indefinitely. The final question on this page is, when is the particle at 4, 2? Okay, so this is speaking of when is x of t equal to 4. So when is x of t equal to 4? So, okay, we can find that by just going back to our graph and looking at the position graph and seeing where it ever reaches a y value of 4. Which would correspond to a position of 4. So let's look at our picture again. Okay, so I'm turning off the derivative. I don't need to see it anymore. So here's my graph. And I'm wondering when y is 4. So remember that these are 10 each on the y-axis. So somewhere right in here, y is 4, meaning x is 4, because this is my position graph. This is my x of t graph. Okay, so to find those points, I'm going to actually go in and under y1, and down here under y3, you notice I've turned the derivative off. I'm going to just put 4, and I'm going to graph it. Okay, and I'm interested in these 3 points here. This one, and this one. These are not x-intercepts. These are where those 2 lines cross. Okay, so to find those, we can simply use the zoom feature. And I kind of like the zoom box. I'm going to draw a box around this entire region. This encapsulates that part of the graph. Create an automatic window for that region. Okay, I'd like those 2 points first, and then there's another one over to the right. But I'm going to do a calc intersect curve y1 as my first curve. Second curve is y3. It automatically highlights that when I press enter because y2 is turned off right now. Press enter again. And to guess, I'd say this intersection, because there are two of them, so I'll hold the calculator up. 1.2447. 1.245. 1.245. Okay, let's go back and write that down. Okay, back to the graph. Let's look for that other point. Calc, intersect. That first curve is this one, y1. Second curve, so I pressed enter, is y3. And we're going to guess over here. Right there. 2.126. Put that in. Okay, and then there's one more. So I'm going to have to go back to like do a zoom standard here. I'm going to have to do a Z-box over on the right there. I'm just in this point right now. Okay, so let's do, actually I probably don't need to do zoom box. I got a pretty good visual right now. So I'll just do calc, intersect, and let's just move this over a little bit. Okay, yeah, so my first curve is y1, enter. Second curve, it knows I'm looking at y3, enter, guess, 4.63. .629 seconds. So there are 3 times at which this occurred. Okay, let's look at our motion one more time. Okay, so we had started, remember, at negative 45, 2 at t equals 0. And the object moved to the right. To the point 6.299, 2. And that happened at t equal 1.653 seconds. Okay, the object then turned around, headed backwards to negative 10.373, 2, and that was at t equals 3.680 seconds. And then it turned around one more time and went to the right indefinitely. We talked about the speed. We said that there was a couple times when the speed actually was increasing, but it was not necessarily when the velocity was increasing only. So let's talk about this. If an object is moving to the right, but it plans on stopping, it's going to have to start slowing down. Okay? So you can't say the speed is increasing just because it's moving to the right. It's starting to slow down. It has to make this stop. Okay, here this is speeding up. It's going backwards, but it has to speed up. Otherwise it can't. It can't go the other way if it doesn't speed up. Okay, right here is an interesting point we didn't talk about. at this point in time, it's at a constant speed. I should say constant velocity right there, just for a split second. That point there is when the acceleration is 0. Okay, and then it had to slow down, see, to get to this point. And then turning around, it speeds up and goes forever. So when was it speeding up? Well, it was speeding up to begin with. But then it had to slow down, stop, speed up. It has to slow down again in order to stop. And then it speeds up again.